everybody. I'm David Hall. I'm the research engineering lead at Stanford Center for Research on Foundation Models. Today I'm going to talk to you about Levanter, which is our framework for training foundation models. So I don't think I really need to tell anyone here that foundation models are already having a massive impact in the world. ChatGPT reached 100 million users after just 2 months, making it one of the, I believe, the fastest adopted product of all time. Congress is obviously very, and the EU are very interested in regulating this space. And of course, these models, one of the things that distinguishes these models is how much compute they require, and therefore how much cost they require. GPT-4 is rumored to cost around $100 million, and we see similar size investments from companies like Google and Anthropic and Meta and pretty much everyone else these days. And that kind of raises a question of, oh, mic up, great. All right. That raises a question of what should the role of academia be in this new world? We obviously can't train, even a university like Stanford can't train a $100 million model on the regular. So how can we still be relevant in this world? So in 2021, Stanford established the Center for Research on Foundation Models and coined the term foundation model. And it's a massive interdisciplinary collaboration with across more than 10 departments with over 30 faculty, a few hundred students and postdocs, what we do at CRFM is divided into 3 groups. There are applications, like working in, say, biomedical domains where we have unique data sets. We can collaborate with the Stanford Hospital to develop models that will help them improve patient care. There are, of course, deep technical advances, things like flash attention came out of Stanford. And we can also, think through social responsibility. How should policymakers think about the role these models have in the world? And this gives us some amount of, by being a non-commercial entity, we have some amount of objectivity that for-profit enterprises don't have. Okay, so CRFM has an engineering organization. It's very small. It's just 2 of us plus a few RAs, research assistants. And you might wonder, like, why have an engineering organization at a center like this? And it has to do with the scale, the rate of innovation, and the rate of investment. As it grows, academia has to adapt to keep up, and it requires a lot of engineering infrastructure and resources just to build models and stay relevant. We have 2 projects. We have Helm, which is a platform for evaluating large language models, and it sort of solves the MN problem, so that we've evaluated, I think it's over 60 models now, on more than 40 benchmarks. It's very cross-cutting and holistic. And we also have Levanter, which is the focus of the rest of my talk. And it's a platform for training large language models and other foundation models. And its goal is to be legible, scalable, and reproducible. And one of the fun features of Levanter is actually as fast as many of the fastest commercial frameworks that are out there, including those from Mosaic ML and even those from Google. Okay, so what do I mean by legibility, scalability, and reproducibility? For legibility, we want to demystify what goes into training a large language model or any other foundation model. We want the code to be easy to follow, and we want to be able to separate the logic of the model from the logic of scaling the model. Both of these are very important features, but they often get tightly coupled, and it makes the code harder to follow and harder to adapt. We also, of course, care about scale. The goal we set for ourselves is being scalable, at least up to about 20 billion parameters. Ideally more, but this is the largest that we thought we had a chance of training on the budgets that we have. And it should also be fast, in the same ballpark as the best commercial players. We originally started out with the goal of it being not embarrassing, but we actually did better than that. And then finally, reproducibility. We want to be able to reproduce our results exactly. We want bitwise determinism, meaning that you get the same results every single time, even in the face of preemption and restarts from checkpoints, because most of our compute comes from donated compute and is preemptible. Okay. So Levanter is a new JAX-based code base. It works on GPU and TPU. It places a high premium on legibility without compromising scalability. And the performance, as I've said, is competitive with the largest libraries, even those whose main goal is performance, where what they do is brag about their performance. And of course, we have bitwise reproducibility, so you get the same results every single time. Okay, so legibility. So this is some fairly typical tensor code. It happens to be written in JAX, but if you've written NumPy code or PyTorch code, this code should look fairly familiar. The goal is, this is just evaluating the loss, the mean squared error, between some target y, some features x, and some weight vector w. And this code looks fairly straightforward and standard for anyone who's written this kind of code before, but it's actually wrong. And it won't throw an exception. It will just silently give you the wrong answer. And it can be tricky to see why. And the answer has to do with these shapes of these tensors. So y is 128 wide, but x times w is 128 by 1, which sounds the same, but if you know NumPy or PyTorch or anything else, when you put together 128 and 128 by 1, two tensors of those shapes, you end up with something that's 128 by 128. So you end up evaluating all pairs of differences, and you end up with some meaningless number that isn't useful. And this kind of bug shows up over and over again in deep learning code or in any kind of numeric code. I've had this happen, over a dozen times in my life. I usually lose a day to it every time. And it's an endemic problem. And also this code tends to be, I think, illegible. So this is a library called MinGPT. It was designed to be pedagogical. And I, even as someone who's worked in the space for quite a while now, still have a lot of trouble understanding what's going on. There are comments, but they're prone to bit rot. And you have to really think hard about what's being swapped here. What does -2 mean? What does -1? What are we normalizing over? And then again, what are we swapping? And then we have these views at the end that are very normal, but they hide bugs. If you forgot that transpose, your code would just silently generate the wrong answer, just as we had before. Okay, so tensors with positional axes are bug prone and less maintainable in the same way that assembly language is bug prone and less maintainable than higher level languages. Positional tensors typically overly prescribe the exact set of dimensions of tensors, reducing the reusability and modularity of tensor code. And so what we've done is we built a new library called Haliax that's a named tensor library that improves readability, reduces the risk of bugs, and makes it easy to scale model training to hundreds of TPUs or tens of billions of parameters. So we're gonna make things nicer to read and scale all at the same time. Okay, so the centerpiece of Haliax is this named axis where you pair a name describing the semantics of some dimension with the size. The sizes are the usual things you're used to in deep learning, and the names are the things you would find in the papers, but often don't make it into the code. And we can create named tensors using a very familiar syntax. And we can even do operations like matrix multiplication the same way. And if we take our example from before, we can write code that looks basically the same, but we've defined away the ability to make that broadcasting bug. And so we've eliminated an entire class of bugs and made our code easier to read all at once. And if we take a look back at this attention implementation, where it was extremely hard to follow all the indexing juggling, we can instead have an implementation that almost looks like pseudocode, but it actually implements the exact same algorithm, actually runs, and ends up actually being faster than the code on the left. Okay, so that's cool. Legibility and expressivity are important goals, but we still, to be useful, we have to be scalable and efficient as well. But as I've said, named tensors actually give us both. In fact, it'll actually make scalability even easier to implement and to understand. So probably don't have time to go through the whole concept here, but if we think about our accelerators, our TPUs, our GPUs, we can think of them as actually being a named array all on their own, except instead of having numbers in them, they have GPUs or TPUs. And if we take a matrix like this one, we can think about dividing it evenly across all of the TPUs along some axis. So this is dividing up our input embeds tensor along the batch axis. And this blue, and we can take that conceptual, that idea, and we can implement it in code in this exact way by saying we're going to map the batch axis to the device axis of our devices, and we're going to shard our data across this mapping. And just like that, we've made our codes data parallel, and it can run on as many TPUs or as many GPUs as you can get your hands on. That's pretty nice. But we can actually do better. So one of the state-of-the-art method for training extremely large models these days is something called fully sharded data parallel. You also may have heard of it called Zero. The insight it has is that typically in normal data parallel training, you have a full copy of your parameters on every single TPU, and you only split up your data across each TPU. With fully sharded data parallelism, however, you instead split your parameters across some axis, here the embedding dimension, and you end up with just a single slice of every parameter on every TPU. And whenever you need to do compute, you do gather a network sort of communication so that you send all of the relevant parameters to all of the machines that need them and do your compute. This is a very complex operation that if you look at the PyTorch implementation, there's tens of thousands of lines of code to get this to work. And we can add it to any modeling code in about 10 lines of code in Haliax. Now we just add a parameter mapping, and we shard our model just like we sharded our data. And we can also shard our optimizer states. And in addition to data from before, and now we just give a little bit of extra help for how we do the computation. We want to shard the data during compute to look like the data sharding. And just like that, we've implemented fully sharded data parallel. Okay. So I've shown that you can scale, you can have a legible implementation and you can still design for scalability. But scale means more than just you can represent FSDP. It actually has to be fast and it actually has to scale. It turns out that it does. So this is something called model flop utilization. Don't worry too much about what it means, but it basically means like how good of a job are you doing using the hardware you have available to you. This is measured on a V3 256 TPU pod, which is like 50 A100s worth of compute. And if we look at some comparisons, it's not super scientific because they're different hardware, but we're achieving MFUs that are in the same ballpark and sometimes better than state-of-the-art implementations. These super large models tend to have much lower utilization, so the comparisons of Palm and Megatron aren't super fair. MinGPT, that pedagogical implementation from before, is actually hovering around a little under 20%. So we're actually doing quite well by this metric. Okay, I've got 5 minutes left, I think. So I can talk about reproducibility, but short answer is PyTorch code is actually very hard to get reproducible. This is 4 runs that were launched on the same machine with the same random seed, with all the determinism flags set, and it's still not deterministic. And you may think whatever, but it turns out that it actually can really matter, especially when you're training these really large models. They tend to be very unstable when you're training them. And this is 2 runs that were started from the same random seed in PyTorch, and one of them blew up and the other didn't. And we have no way of tracking down exactly what went wrong because we can't reproduce the run. Oh, I have 15 minutes. Oh, great. doing great. All right, cool. I'll have time to go through fun examples then. Great, great. So in Levanter, however, we get bitwise reproducibility. So this is, again, 4 different runs, same random seed, but this time we're actually going to use different TPUs, different TPU machines, same configuration. And we're actually going to kill the jobs and restart the jobs, and we end up with perfect reproducibility even in the face of these restarts. These are bitwise identical results. And so that allows us to do science. Okay, let's talk about some of the cool things we've been doing at CRFM with Levanter. So the first thing I want to talk about is a new optimizer called Sophia. So most of you who've done deep learning have certainly heard of Atom. It's been the state-of-the-art de facto optimizer for the last 9 or 10 years now. A student named Hong and his advisor Tongyu Ma developed this new optimizer called Sophia. That's a new second-order optimizer that uses an approximation of the Hessian, which is to say the second derivative, to improve the optimization, to improve the optimizer's estimate of what direction to follow. And you end up with an optimizer that is 2 times faster than Atom. And they started out by training small models of about 100 million parameters to maybe 700 million parameters. They couldn't go any higher. And when they put out the results, they got a lot of feedback from industry basically saying, we don't believe that this will scale. This is not something that's relevant to us. We see this kind of stuff all the time. So instead they took Levanter and implemented Sophia in about a day. And scaled it up to 1.5 and then 6.7 billion parameters and showed that it actually does scale and that even out to 100,000 steps, or I forget exactly how many tokens, but probably 50 billion tokens, it's 2 times faster than Atom. So we have this new optimizer we developed that's easy to implement, doesn't require additional memory, and ends up being 2 times faster in terms of step count. And about 1.6 or 1.7 times in terms of wall time, something like that. We also have some fun, we've also implemented controllable music generation. So John Thixton is a postdoc here at Stanford, and he developed an approach to music generation that allows you to give a prompt to the model. And unlike with an LLM, the prompt can be not just a prefix, but it can actually be any infix, or it can be just a single voice, a single instrument from that a human made. And then the model can generate the rest and can generate a rich accompaniment with multiple different instruments all at once. I'm guessing sound probably isn't going to come through, so I'll skip the audio demo. But the upshot is that the results are for accompaniment generation are every bit as good as or rather are indistinguishable from humans, at least according to some carefully vetted Turkers. So that's pretty cool. And then just to talk just a little bit about some of the new things we've implemented. We've improved the documentation. Things should be easy to get started out of the box on GPU or on TPU. We also have released support for Llama and LoRa, so you can train an alpaca with just a couple lines of code. And we have an implementation of flash attention 2 that allows you to scale up sequence lengths from the normal like 2048 or 4096 that people do these days, all the way to 32,000 without too much trouble. And coming soon, we're working with NVIDIA right now to fix support across multiple GPUs, across multiple machines. Currently, you can run Levanter and it works great on a single machine with 8 or even 16 GPUs in it. but there's some network bugs. We're also working on adding do-re-mi, which is a new technique that was developed here at Stanford that will automatically tune the training mixture to be optimal for the kind of model you're trying to train. We're also improving the flash attention implementation so that it can automatically tune itself for whatever the hardware is that you're using. And soon we'll be adding vision transformers so that we can train not just large language foundation models, but vision models or hybrid language vision models. Since I've got a little bit more time, let's get backpacks. I'm going to talk about Lumia. So one of the projects we're training at Stanford in collaboration with Stanford Hospital is Lumia. And we're going to take about 3 terabytes of patient data that's been carefully anonymized. That includes all of the notes and test results and also all the diagnostic codes that doctors use. And we're going to use it to improve diagnosis, do what's called risk stratification, trying to figure out who's likely for a repeat visit to the hospital. Do things like history retrieval so that doctors don't have to go scrounging around in the medical records for forever. And we started the training run for sort of the first phase of this just the last couple days ago. I'm really looking forward to the results of this in the next few months. Yeah, I'll cut it here. Yeah, thanks.
We've got some time for questions. I can run mics.
So what do you think is the innovation behind of the framework that you guys building now that other libraries like Keras are multi-backend and you can pretty easily use a friendly API to create models and just switch from one backend to another, like PyTorch or JAX, or what do you think that this could be the benefits of use? One of the
So it was a little hard for me to hear just with the speaker. I think the question was, what was the motivation for choosing JAX and choosing our own framework? Yeah, it's a great question. The reality is that most people in academia are using PyTorch still, but Google generously gave us access to a large number of TPUs for free. And we started off trying out PyTorch on TPU, and support was preliminary, I guess, maybe the right way to put it. And it didn't seem like you could train anything of any size using it at the time. And so JAX allows us to be opportunistic with our compute. NVIDIA, as I've said, is working with us to make Levanter sort of first class on their hardware, and we're possibly going to talk to other organizations like Intel and ARM who are building their own accelerators, and allows us to sort of take compute wherever it comes from.
Cool. Thank you.